Hello, Danish. Good morning. Good afternoon.
Hello, are you able to hear me?
Yeah, I'm
Okay,
able to
okay,
hear. Yeah,
okay. Let me start the recording. Okay,
yeah. Maybe others can, like, maybe we can wait for some time for the others to join.
okay. They will join later on. I will start the lecture. Okay.
Okay. Yeah,
Is presentation visible?
yeah. The presentation is visible.
Okay, thank you.
Yeah,
So, good afternoon, everyone. Welcome to the week 7 of live sessions on finite element method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, today is our 7th week of the live sessions, and in the past couple of live sessions, we were seeing the formulation for the bar element, and then we extended that formulation to the truss member. So in last class, we saw the formulation for a truss member in 2D. That was in 2D truss. If you remember from the last class that for a 2D truss, there were having 2 degrees of freedom at the two nodes. One at one single node, there were having 2 degrees of freedom. One displacement along x-axis and another displacement along y-axis. So if we continue that system into 3D, we will be having one more degree of freedom along that direction. So I thought that's not important. You can do that thing at your own place. You can see the analysis of a 3D truss as there is only an increase in 1 degree of freedom. And we also have very less weeks left for the discussion. So I will be directly jumping to the beam bending because that is very important so far as this course is concerned. You will be having questions there in the beam from the beam bending as well in the examination. So let's talk about beam bending in today's live session. So you people all are aware of a beam in our structural member that is beam is one of the structural members like our columns, like slabs, like girders. Beam is also a structural member. And for the technical definition of the beam, it is defined as a structural member that carries transverse loads along its axis. And if you see the same for a column, it is a member that carries axial loads along its axis. So for example, uh, I will write first for a beam. Beam is actually a structural member that carries loads along transverse transverse direction to its axis. Okay, so we all are aware of this structure that we show more commonly in our structural analysis. Like this is a beam structural member, and if the loading on this structural member is in such a way like it is transverse to its axis or perpendicular, we can say that loads are like this. It's having some inclination theta P1, P2, P3, P3, and if you see its axis like this is the neutral plane or the neutral axis, you see that these loads are acting in transverse direction to this axis. So we call this structural member as beam. So in structural analysis, we have seen a number of methods of analyzing a beam. So for simply supported beam, what we did is we first find the reactions at the supports, and then we compute the shear force and bending moments at any section. Similar type of analysis is here in finite element method. we can analyze these beams. But here we cannot have a simple, like as I already told you, the beauty of the finite element analysis is that it can incorporate complex boundary conditions. Like in structural analysis 1, structural analysis 2, we were given the boundary conditions like simply supported, fixed, or fixed, and then one more support at the middle. These are very simple boundary conditions, and we have classical solutions for these boundary conditions. So in finite element analysis we can have different boundary conditions, whatever there exists in the real life problems. We can incorporate those boundary conditions in our problems, and we can solve those problems with the help of finite element analysis. So in today's lecture we will be first seeing the formulation, how we deduce the element equation for a beam element, like it is stiffness matrix, it is nodal force vector, and other things, and then we will solve a problem regarding that. So for example, if we consider a beam element like this, mm, and I already told you that in finite element analysis we can incorporate complex boundary conditions as well. So for example, if we have a complex boundary condition like complex geometry of a beam element like this, so it's having loading pattern like this is its axis, and it's having something varying loading like this, okay, and loading is in upward direction like this. This is its x-axis, this is its y-axis, okay, y-axis like this, and it's having a varying load q of x acting upwards in direction. And if we cut a very small element dx of width, dx very small with dx, and we see what, and we detach this element from our main beam element and see its equilibrium like this. So this is our beam element, assuming its cross section at that point of time to be this rectangular. So it will be having a very small loading like this. So it's again having q of x loading, okay, q of x. And since we detached it from a structure which was stable, which was in stable equilibrium, so we have to show the forces, internal forces as well. So like from this side, moment will be like this and shear force will be like this. You already know these things from simple bending theory. And if we move to the other side, there will be an incremental increase V plus dV in shear force, and same in the bending moment as well, M plus dm, okay, M plus dm. So before going forward, we have to choose the sign convention, what sign convention we will be following in our formulation. So sign convention for the formulation is like that: this is our beam element. So if the applied forces, we will be taking these applied forces as positive. So forces acting upwards at the two nodes will be taken as positive, and moments like this is in counterclockwise direction, and this one is in counterclockwise direction. These moments will be taken as positive, okay. This is applied forces, okay, applied nodal forces, and regarding the internal forces, how we will be taking the sign convention for them. Internal forces, first internal force is the moment. Internal, I mean to say that variables, first is the moment and another is the shear force. So for the moment, these moments we will take in positive, okay, internal moments, which are like this, okay, these will be positive internal moments. Similar for the internal, one more internal variable, that is shear force, we will be taking this shear as positive, okay, one acting, this one from this side like this, and this from this side like this is positive internal shears, okay. So for this element, if we write the equilibrium condition, that is summation of Fy to be 0. Let me take this with me because we will require this. Okay, we have this thing, we have to see the equilibrium of this thing. Okay, okay, we have to see the equilibrium. So if we write summation of Fy to be equal to 0, and we will take positive upward direction to be positive. So the first force that comes out up to be first upward force is Q times dx. Actually, this is dx. Okay, this is with the dx. First force comes to be Q times dx. Then we have one more shear acting upwards, that is plus V. Then we have minus V plus dV acting downwards, that is its sign is minus. It is equal to 0. If we evaluate, we will see that the variation of the shear force with respect to length dV by dx is given by distributed load. Well, you people know it from the strength of materials concepts. Okay, then we will take one more equilibrium condition, that is summation of moments to be equal to 0, and in which I will take clockwise moment, anti-clockwise moments to be positive. Okay, anti-clockwise moments to be positive. So first, this equation will yield, first m is clockwise, so it will be minus m. Then this will create clockwise moment, v will create clockwise moment again, it is minus v dx. Then we have this will again create, this q dx will again create clockwise moment, so it was minus q dx. This is force and its lever rm is dx by 2, and we have anti-clockwise moment plus m plus dm. Okay, m plus dm to be equal to 0. If we neglect the dx square term, this term dx square, if we substitute it to be equal to 0, this equation will yield us dm to be equal to v dx. Okay, or the gradient of the bending moment is given as a shear force, or dm by dx to be equal to shear force. You also know it from the strength of materials concept. Okay, then dm by dx is equal to v. Okay, so again differentiating it with respect to x, we have d2m by dx square is equal to dv by dx, and dv by dx is equal to q here. Okay, is equal to q. So first of all, we established this relationship, that is curvature, shear force, and distributed load. What is the relationship between them? And then if we see that under the influence of the given loading, so if we see that this was, if we see a beam element, same dx beam element like this was the beam element earlier, like this. So let's consider this is continued from this side. Okay, from this side as well, from this side this is continuing with the beam. Okay, and if we assume its neutral axis to be like this. Okay, neutral axis to be this, so this is a dashed, and this is neutral axis. Then what else is, we consider a point a within this beam element like this, which is at some distance y from the neutral axis. Okay, some distance y from the neutral axis. And if we see after bending what will happen to this point and what will happen to this beam element. So for example, after bending, this beam element rotated like this, there is rotation as well as transverse displacement as well. So in beam, you know that thing is there. Okay, same beam. So this is like this is like this. We have to take it a little bit here. So, and we are assuming that plane sections before bending will remain plane after bending. So there will be neutral axis will be like this. Again, neutral axis will just rotate, and let me draw it a little bit below. Okay. Then what else is there? So this A point will shift to some point B. I will draw a line like this, connecting this point and this point. Okay. Connecting this and this. Okay. So this point shifted to now another location. So this was A point. Now this is shifted to this location after bending B. Okay. Such that it is having both x displacement as well as y displacement. So it's if we see this is uh, like this is x axis, this is y axis. If we see how it is being displaced, so you can clearly see that this is its u displacement. That's x axis displacement u, and this point shifted from this point shifted from this place to this place. So this will be clearly its transverse displacement, that is v. Okay. And one more thing, there is a rotation of this point as well. So this is like this. If we see that thing, so this is there is a rotation. So this point rotated by some amount, which we will give as, so this will be, if this is theta, so this neutral axis will also move by the same amount. So this neutral axis, sorry, neutral axis will also move by same amount, or rotate by same amount, in fact. So this is theta as well. We consider this small triangle where this, so directly we can write this theta to be equal. So since this theta is the rotation or the slope, you know that slope is given as dy by dx, or dv by dx. Y is here v. Okay, so our slope will be equal to dv by dx or dv by dx. Okay, so these are the things here. And so we can write this u, small displacement u, to be equal to x-axis displacement u to be equal to, so this is minus times, this shifted to the left side like this, so this is minus times y multiplied by the slope dv by dx. Okay, dv by dx, and I can equivalently write it as minus y dv by dx. I will write it by v small subscript x. It represents the first derivative. Okay, vx. Okay, also from the strain displacement relationship, we know that strain epsilon x is the gradient of displacement du with respect to x du by dx. So I can write equivalently in place of u, like u I can replace by this. Okay, I can write d by dx of minus y dv by dx. Okay, it is minus y d2v by dx square, or I can equivalently write it as minus y vxx. Okay, you keep these expressions in mind. Okay, and from Hooke's law I can directly write stress sigma x to be equal to E epsilon. Okay, where I am choosing E to be constant. Okay, so if I can write sigma x to be directly equal to minus E y v x x. I just substituted the value of the strain y minus y v x x minus y v x x x. I substituted here. Okay, so I got the relationship for sigma x. Okay, so now we have to compute the moment mx. So mx is given by, you know it, mx is given by minus times. So since this is coming out to be what, minus times, we have to compute the all the normal forces acting at that point. That is sigma x is the stress there, and what will be the area? Area will for this element, small element, is dA. First I will write dA, and what is the lever arm I am considering here at this point? Lever arm will be this y. Okay, you can understand it from this concept, or we have this expression directly from the simple bending theory. Minus sigma xy dA over the element area A. Okay, and I can substitute the value of sigma x. Comes out to be E y v x x dA y dA E y v x x y dA. Okay, I substituted sigma x to be equal to minus E y v x x. Okay, that is E y v x x minus minus plus y dx. Now that will be equal to, it will be equal to, since E is constant and vxx we can take outside. Okay, vxx like this, then we can take this y square dA over the area A. So if you remember this term y square dA, or I will highlight it, y square dA is given as the second moment of area. Okay, it is given to be equal to I. So our moment m will come out to be E I V X X. So this is the expression for the bending moment at location Y. Okay, I will write here I, where I is equal to integral over area A y square dA. Moment of inertia of, of a cross section. Okay, then moving forward, we can write this EIVXX in our previous equation, this d2m by dx square. Okay, then we can equivalently write as d2 by dx square of EIVXX. EIVXX to be equal to d2m by dx square. Okay, which is in itself equal to dv by dx, which is itself equal to the distributed load q of x. Okay, I hope this point is clear to you. So we developed a relationship between all these quantities within a beam element. So if we see these two parts of this equation, we will see this part, okay, and this part q of x. Okay, we can write then d2 by dx square of e I v x x minus times q of x to be equal to 0. So this is the beam equation we have. It is a fourth order differential equation in variable v. Variable v, that is transverse displacement. Okay, transverse displacement. And the boundary conditions for this fourth order equation, there will be the four boundary conditions. Can be physically the boundary conditions that can be specified are there will be transverse displacement v specified, or rotation theta specified, or either bending moment or shear specified. 1 second. So what will be the boundary conditions for it? So there can be physical boundary conditions for beam. So for example, this is our beam element like this. So either at one end there can be transverse displacement, that is v specified, sorry, transverse displacement v can be specified. Okay, v can be specified, or the rotation at this point. Okay, theta can be specified, and theta we write as vx. Okay, that is the first derivative of transverse displacement. It can be specified. It is rotation. Okay, or there can be other boundary conditions that will be given at that node. Either you will be given the bending moment at that point, like the moment acting at this point, m. M can be specified. We know that moment is given as EIVXX, bending moment. Okay, or we will be specified with shear force as well. Okay, this is V, shear force, and we know that its expression is EIVXXX. Three times differentiation. It can be specified, shear force. Okay, so any of the four boundary conditions will be given for our beam. So we will be then able to solve the different beam problem, with the given differential equation that we derived d2 by dx square eivxx minus qx. Now we have to formulate the element equation for from this differential equation with the specified boundary conditions. So we will use that the same variational principle like we used it in uh, earlier lectures, like how that's Rayleigh-Griggs method, that's multiplying the whole differential equation with the variation of the primary variable. That's here the primary variable is the transverse displacement, and then taking the integral over the whole domain, whatever will be the domain of the equation, and then finding the functional and minimizing that functional with respect to the unknown variable. Then we can get so as the error should be as minimum as possible. So we will be using the same formulation. So our first goal is potential energy functional. We have to find that potential energy functional of beam. Okay, so we know that our beam equation is d2 by dx square of ei vxx minus q is equal to 0. Multiplying by both sides is delta variation of v and integrating over the domain. So for example, the domain is dependent from x1 to x2. These are the two domain points given as. So then we have d2 by dx square ei vxx minus q whole multiplied by the variation of v, that's equal to 0. So we will integrate this by parts. Okay, this term by parts, that's integration by parts IBP. Okay, we will integrate it by parts. While integrating, we will get the expression like this: variation of v d by dx of eivxx, this from x1 to x2. Then another point we will get from integral of x1 to x2 minus times d by dx. So we have to differentiate eivxx. We have to differentiate this. We will get first by integrating eivxx first this, and then we have to differentiate del v d by dx of del v, variation of del v minus q del v. Okay, so the integral is on this part as well. Okay, so I just combine it the both things, just keep track of all the things. Dx to be equal to 0. Now we can write d by dx of variation of v of x to be equal to variation of d by dx of v of x. I told you these identities in the first class. Okay, not variation of v. Okay, we can write as the variation of v, which is equivalently written as variation of v of x. So we will use this this thing here. We will use this thing here. Okay, so if we use that thing, we will get the same thing back first, that the variation of v d by dx of eivxx from x1 to x2, this will be minus uh, then this term again we have to integrate by parts, this thing. Okay, we will again integrate it by parts. We will get variation of vx eivxx. Okay, so we will take this as first term, this whole as first term, and this whole as second term. Okay, so first we integrated it eivxx from x1 to x2, sorry, from x1 to x2. Then there will be one more part of this integral, that is minus minus, it will be plus, that will give us as x1 to x2 ei vxx. Okay, for integrating it, and then we will be having again d by dx of del vx. Okay, we have to differentiate this term and integrate this one. So here we integrated and this kept as it was. Okay, and combining this with by q variation of v dx to be equal to 0. Very long expression. Okay, now we have to use the terms like input term of ei this actually eivxx, in the place of eivxx we have to write m, that is internal moment. Okay, in place of d by dx of EIVXX. Okay, VXX. We have to write V because that is the formula for internal shear. I showed you in earlier. And one more thing, I'm using this variational identity here. That is with the variation of 1/2 of EIVX x square will be equivalently written as EIVXX VXX d by dx of del Vx. Okay, so we will be using it this expression here. Okay, in place of this we will write del 1/2 of EIVXX square. Okay, when we substitute all these things in our this, so what I will do is I will highlight it like this and substituting here. Here, if we do this substitution, what we will get eventually, we will get first that the variation of V and shear V, don't confuse between small v and capital V. Small V is the transverse displacement and capital V is the internal shear from x1 to x2, then minus variation of small vx, then moment x1 x2 x1 x2 plus integral of x1 x2. I told you what substitution I'm going to make, so I'm writing that variation of 1 by 2 of EI VXX square. So I will close it like this, minus variation of QV, it's with respect to dx to be equal to 0. Okay, so we can take both these variations common. So our equivalent will be variation of small v capital V from x1 to x2 minus variation of v of x moment m x1 x2 plus the variation of integral of x1 x2 1 by 2 of EIVXX square VXX square minus QV dx to be equal to 0. Okay, so what we will do is that this transverse displacement is chosen in such a way that we have essentially, I forgot to told you, transverse displacement and Vx, that is rotation. These are essential boundary conditions. Okay, so these are specified, these are chosen in such a way that is, sorry, the admissible trial solution for this differential equation will be chosen in such a way that is that the value of this transverse displacement and the rotation will come out to be 0 at the domain points, that is x1 and x2. So we will be substituting the value of x1 x2 here, x1 x2 here. So our their variation, that is del v and del vx, both are equal to 0 at x1 and x2 because trial solution is chosen in such a way. So if this vanishes at the boundary points, then our this will become equation will become variation of from x1 to x2 1 by 2 of EIVX x square minus QV dx whole to be equal to 0. Okay, So you are seeing that there is only one term in the variation. So we call, if you remember from the really exist method, we call it the functional. Therefore, our functional is, we represent this functional to by pi p, because actually it equivalently represents the strain energy within this total put energy in this beam after it's bended. Okay, pi p as a function of transverse displacement v is given as from x1 to x2 one half of ei v x square minus q v integrated with respect to dx. Okay, this is the equation of our functional. Okay, so this functional. So if these were essential boundary conditions, if these were specified, if essential boundary condition were specified. So for example, if natural boundary conditions were specified, that is either shear or bending moment was specified. If natural boundary conditions, natural boundary conditions in our problem, that is either shear or bending moment are specified, then we have to use those things. Okay, so since there is a different sign convention for the internal forces and the external forces, as I already showed it here, sign convention here, applied forces and the internal moments and internal shears. So equivalently, if these are specified, then what will be the shear force V of x1? So for example, this is our beam element. So if we are given that force F1, nodal force F1 is acting here and nodal force F2 is acting here. Okay, and you are also given that it is being acted by a nodal moment M1 here and another nodal moment M2 here. Okay, applied, this is applied. Okay, applied force at beam ends. So equivalently, if we write them in terms of internal forces, so because of the sign convention, so what will be the shear at this end? Shear will be V1 will be equal to F1 because they have same sign, same direction. But V2 here, shear is in opposite direction, so V2 will be given as minus F2. If you see the sign convention that I showed you earlier, and the internal moment is opposite, so this moment will be given as in same direction but minus M1, and M2 is in the same direction as the internal moment M2. Okay, M2, this is with sign convention for internal shears and moments. So if we see that using this, we can see that the this shear force at point x1 is equal to F1. So this is x1, this is x2. So if you see Vx1 is equal to F1 and Vx2, this is capital V, okay? Remember that. Vx2 is equal to minus F2, okay? And our M moment at x1, Mx1 is equal to minus M1 and moment at x2 is equal to M2. So if we have to use these things here, that is Vx1, Vx2, Mx1, Mx2. So we will substitute these values. Substitute these values so that our equation will finally come out to be uh, so this is A. Okay, I will write substitute in A. Okay, so if we substitute it in A, that will equivalently will become variation of V at x2 times f2 minus variation of v at x1 times f1 minus variation of Vx at x2 times moment m2 minus variation of Vx at x1 times m1. Okay, and it will be our plus our potential, this whole function. Okay, so we denoted it by pi p of v. Okay, so it will be plus variation of pi p as a function of v to be equal to 0. Okay, so our functional for the beam, so total, if we take the variation from whole common, variation times this is displacement v at x2, that is small v2, transverse displacement, v2 f2 minus v2 f2 minus v1 f1 minus uh, minus this is vx2, that is theta 2, actually theta 2 m2 minus theta 1 m1. Okay, actually you have to write small vx1 is equal to v1 and vx at x1 is equal to theta 1. Hope you are following. Vx2 is equal to v2 and v small x at x2 equals theta 2. Okay, theta 1 m1 minus pi p of v to v equal to 0. So this is again the variation of something is equal to 0. So our functional will become, if natural boundary conditions are specified, our functional will become functional. This will be again another pi p dash of v. If natural boundary conditions are specified, it will be integral of x1 to x2 1 by 2 of e I v x x square e I v x x square minus qv dx minus times all this thing v1 f1 plus v2 f2 plus theta 1 m1 plus theta 2 m2. Okay, this is our functional. So if you will clearly see in this thing what all the terms represent, so actually this term represents, this is beam strain energy. Okay, if you see, it is resembling with the expression of the strain energy, and what this thing represents is with the integral, it is actually work done by the external loads, work done by q of x, that's the distributed load. And what is actually this whole thing, this is simply the work done by the external forces, work done by external forces, that is f1 f2 and moments as well, m1 m2. Okay, so we derived the expression. So the total potential for our, this is pi p of v, that is pi dash p of v is actually equal to strain energy SE. This is strain energy whole, strain energy minus work done by applied forces. Okay. Then, for example, if we consider a two-node beam element, okay, now we have to derive the element equation as well. So, for example, we considered a two-node beam element like this. Two-node beam element like this. So, for example, it is having the degrees of freedom. It will be obviously here. It will be transverse displacement v1, and it will be having one rotation theta 1. I already showed you theta 1, and it will be having transverse displacement at and v2 and rotation theta 2 at that end, theta 2, and it is having some distributed load q of x as well in upward direction. Okay, q of x. Suppose this we are taking as x-axis and this we are taking as y direction. Okay, and this is x1 point, this is x2 point, and the length of this element is L. Okay, again in the last class I told you we have to change the coordinates. So our coordinates is from x1 to x2. We will change it to s coordinate system, which varies from 0 to 1. Okay, because it's helpful in integration later on, numerical integration. So for that, if we do this interpolation, we will get s to be equal to x minus x1 divided by L. Okay, if we differentiate it, we will get ds to be equal to 1 by L dx. Okay, and we will get ds by dx to be equal to 1 by L because we require it later on. Okay, so if you see our this beam equation like this, where it is. So beam equation is actually a fourth order differential equation. Okay, so fourth order differential equation. So if for one given element we have to assume the trial solution, so the trial solution should be of at least degree 3, that is it should be a cubic polynomial for to satisfy the differential equation. So let us assume the trial solution for the beam element in terms of transverse displacement as s as variable to be a naught plus a1 s plus a2 s square plus a3 s cube. Okay, s cube. So our dv by ds will come out to be dv by dx, sorry, dv by dx. We have to find dv by dx. Our dv by dx will come out here to be dv by dv by ds, because v is a function of s multiplied by ds by dx. Okay, so if you will see ds by dx is already 1 by L, so we will write ds by dx to be equal to 1 by L and differentiate this function with respect to s. We will get a1 plus 2a2s plus 3a3s square. Okay, okay. So at x1, that is equivalently s equals 0, we are given as v of 0 to be equal to v1, because this is s is equal to 0, this is s equals 1. So at s is equal to 0, v of 0 is equal to v1, which implies that if we substitute it here in this equation, we will get a naught to be equal to v1. Similarly, if we see at s is equal to 0, we are seeing these conditions. V dash of 0, that is equivalently is theta 1, which implies that a1 is equal to L theta 1. Okay, similarly we will see, at s is equal to 1, that is at x2 point. Okay, s is equal to 1, v of 1 is equivalently is equal to v2. If we substitute it there, we will get one more equation, that is a2 plus a3 is equal to v2 minus v1 minus L theta 1. Similarly, we will see v dash of 1 to be equal to theta 2. We will get an equation of 2a2 plus 3a3 to be equal to L theta 2 minus L theta 1. Okay, if we solve these two equations simultaneously, we will get the value of a2 and a3. Okay, from this, a2 is equal to minus 3v1 minus 2L theta 1 plus 3v2 minus L theta 2, and a3 we will get 2v1 plus L theta 1 minus 2v2 plus L theta 2. So when we substitute all these things in our V of S, so V of S, when we substitute A naught, A1, A2, A3, we will get something like this. We'll get a large expression like V1 plus SL theta 1 uh, plus S square times value of A2 plus S cube times value of A3. If we write it in terms of V1 theta 1 theta 2, we will get a equation like this. V of S to be equal to, I will equivalently write it as N1 times N1, N2, N3, N4 and variables V1 theta 1, V2 theta 2. Okay, here I will get the values of N1, N2, N3, N4. These are known as these are known as beam shape functions. Okay, so if you remember in the bar element, we have bar shape functions, two bar shape functions. So we're having 2 degrees of freedom. So two shape functions. Where here we have 4 degrees of freedom. So four shape functions. And the value of these shape functions is n1, which will be the function of s. It is given as 1 minus 3s square plus 2s cube, and n2 to be equal to L times S minus 2S square plus S cube, and N3, which is again the function of S, this is again the function of S, to be equal to 3S square minus 2S cube, and N4 of S is equal to L times minus S square plus S cube. Okay, this is N2 of S. So we reduced the shape functions for our beam element. Okay, like this. And similarly, we can deduce the equations for other things as well. Like for the rotation, v of x, we will get this. Like for rotation, we got v. Now we have to find the v dash of x. So vx will be equal to dv by dx, which is equivalently written as dv by ds multiplied by ds by dx. So if we perform this, it will be ds by dx is already 1 by L. So dv by ds. Okay. So now you have to differentiate this with respect to s. That is the shape function you have to differentiate. So you will get your rotation theta to be v to be equal to 1 by L. Okay. Minus 6s plus 6s square. Sorry, I will write it like very simple form. You will get this to be equal to n1 dash, n2 dash, n3 dash, n4 dash to be equal to theta 1 to be equal to v1 theta 1, v2 theta 2. Okay, and n1 dash, n2 dash you will get from this. Okay, and similarly you can get this as well, v double dash. So v double dash you can get, I will directly write vxx you can get as 1 by L square to be equal to minus 6 plus 12s, another L minus 4 plus 6s, another element you will get 6 minus 12s, another element L times minus 2 plus 6s, and you will get again your nodal vector as v1 theta 1, v2 theta 2. Okay, I will equivalently write it as b transpose d. Okay, this matrix I will write b transpose d. Okay, so here d is this matrix and b transpose is this matrix, whole matrix. Okay, so If I have to find Vx square, I have to just take the transpose of this vector Vxx transpose times Vxx. Okay, I showed you this in the last class. So it will be D transpose B times B transpose D. Okay, so all these are actually matrices, or simply we can say these are vectors. So strain energy in the equation, our strain energy is given as this 1 half of EI Vxx square. So that's why I required Vxx square. So beam strain energy, U is equal to 1 half of x1 x2 EI Vx square, Vxx square. I can write equivalently this as 1 half of D transpose will be outside integral changing to s coordinate 0 to 1, x1 to x2 is this is EI B transpose transpose LDS times D. Okay, DD. Okay, I will write it equivalently as 1 half of D transpose K D. Okay, where this K is actually this K is actually this K is equal to 0 to 1 EIBB transpose. Okay, BB transpose, these are matrices BB transpose LDS. Okay, if you compute this integral, you will get easily this stiffness matrix for this no beam element. So K is known as stiffness matrix. Stiffness matrix. So stiffness matrix we computed for our beam element to be equal to EI by L cube. If you perform this integration, put the value of B transpose, and EI is constant, you will get EI by L. You will get the values as 12 here, first element 12, then 6L, then minus of these two elements, minus 12 minus 6L. Okay, then you will get 4L square here, then you will get minus 6L here, and 2L square here. Okay, here you will get 12 minus 6L, and this last element is 4L square. I have not written these elements from this side because stiffness matrix is symmetric, so I will write symmetric. So this is the stiffness matrix for our beam element. So if you perform the same analysis, we will get the value of other things as well. That is the nodal vector, nodal force vector. So nodal force vector, another quantity in our element equation is nodal force vector. We will get RQ to be equal to 0 to 1 Q times shape function vector N LDS. If you perform this integration, you will get a nodal force vector to be equal to QL by 2 QL square by 12 QL by 2 QL square by 12 minus QL square by 12. So this is nodal force vector. Okay, and external forces are also given as external loads that are acting on over this system, that is external force vector, that is RF. RF we already know that. That will be either F1 M1 F2 M2, and in the formulation you remember this nodal vector D to be equal to transverse displacement V1 theta 1 V2 theta 2. Okay, these are the quantities you have to remember. So our equation finally becomes like this. So we have to write our equation becomes K times D is equal to RQ plus RF. This is the element beam element equation. So actually, I directly arrived at this. There was few steps in between. I directly arrived at this equation because we will be only requiring this thing for solving our problem. So since the time is already over, in the next class, I will be solving one problem regarding this beam, and we'll be telling more things about this equation, how to compute the shear force, bending moment, and other things from it. And then we will be solving one beam problem with the help of this element equation as well. Thank you everyone for joining this session.
Okay, thanks. Thanks. Yeah, bye.
Bye. Thank you.